This video is a continuation of the previous post on how to convert the 2D coordinates of the mouse to 3D coordinates of real objects in the word space. Here we focus on converting two-dimensional coordinates of the mouse, considering zooming and panning into two-dimensional coordinates in the word space. While the mouse provides coordinate in pixel on the screen, we aim to select a two-dimensional point or object in the word space, defined in meter or feet. I'll demonstrate how a series of transformation can achieve this, allowing a two-dimensional coordinate of a word space object to be converted into two-dimensional coordinate of the mouse or a screen space with zooming and panning actions. I will demonstrate how to convert a two-dimensional point to a two-dimensional point on the screen, considering zooming and panning, using a numerical example and applying it to the code of a graphical program. Additionally, I will discuss concepts such as word space, clip space, and viewport or screen space, along with transformation matrices. Additionally, I will provide some coding examples related to our topic. The primary question of our research is as follows: how can we convert the two-dimensional coordinates of the mouse in the view space to the two-dimensional coordinates of real objects in the word space? Given that the computer screen is the two-dimensional space, clicking on the screen yields only the x and y values of the screen pixels. However, our goal is to select a two-dimensional object in our scene or word space. This mapping should also function seamlessly after zooming and panning using the mouse. Our proposed solution involves a series of transformation of a two-dimensional coordinate of objects in word space to convert them to the two-dimensional coordinates of the mouse or screen space. Specifically, our two-dimensional object is a plan view of a structural moment-resistant frame of a concrete building. We aim to convert the coordinates of a base point of a column with coordinates of 5.32 and 0 meter to two coordinates in the screen space. This is the ConctiTeller software capable of generating structural drawings. On the right side, we have a three-dimensional model of our building, and on the left window, we have a two-dimensional plan view of the structure. I have displayed the mouse coordinates on the text property of the form, allowing us to observe the mouse coordinates as we move the mouse. One application of mouse picking and converting to word coordinates is the selection of objects in the two-dimensional word space using the mouse, allowing with zooming and panning actions. For simplicity, let's convert the coordinates of this point, which has x and y coordinates equal to 5.32 and 0 meter, to mouse coordinates of e.x and e.y in the screen space. The transformation path is depicted in this slide. We begin with the coordinate point in word coordinate space and translation it to the clip coordinate space using the scale and translation matrices. Then we convert the coordinate to viewport or screen space, which represent the mouse space using the translation matrices. The first step of our transformation involves converting the coordinates of points from word space to clip space. This entails transforming the origin of the word coordinate system to the clip coordinate system. Essentially, we aim to determine the coordinate of point 1 when measured from a new coordinate system with its origin located in the center of the screen window or form in clip coordinate system. Based on our assumption, the coordinates of the top left point of the screen window are represented by P1x and P1y, and the coordinates of the bottom right point are represented by P2x and P2y. Thus, the origin has a distance of P1x from the left side of the form and P1y from the top of the form. In the clip space coordinate system, the coordinates of the top left point of the screen window are -1 and 1, and the coordinates of the bottom right points are 1 and -1. Essentially, the total length and height of the frame are 2. Therefore, to transform the word space to clip space, we need to scale the dimensions of the frame by a scale factor of Sx and Sy, and translate the coordinates of points and origin by the translation of Tx and Ty. The scale factors Sx and Sy correspond to the ratio width and height of the screen window in clip space to word space. The translation factors Tx and Ty represent the lengths of vectors that translate the word space to clip space. These matrices can be combined by multiplying them. The TLX and TLY represent the total length of a screen window in word space, and they are determined by factors such as structure's dimension, margins, and bubble size in X and Y directions. In our scenario, with the form width and height being 758 and 780 pixels respectively, TLX and TLY correspond to 33 and 33.96 meters, maintaining the same ratio as the width over height. By plugging in the input values into our formula, we can derive the values of scale and translation factors. We can calculate the transformation matrix by inputting the values of the parameters. Then we can determine the coordinates of point 1 in clip space by multiplying the transformation matrix by the word coordinates of point 1. In the next step, we should apply another transformation from the clip space to the viewport space. Essentially, we want to find the coordinates of points based on pixels, which is the unit of measurement for the screen or mouse. With a simple equation, we can convert the coordinates from clip space into viewport space, assuming the width and height of the form are 758 and 780 pixels respectively. The X and Y coordinates of the mouse will be 214 and 425 pixels. In the final step, we apply zooming and panning actions of the mouse. In most cases, we need to zoom and pan the view of the model, which must be considered during our transformation process. Zooming action can be represented by a scaling matrix where SCL is the zooming coefficient, for example 1.11 and 0.9, and it can be applied using the mouse wheel action. Panning action of the mouse can be accounted for by translation parameters offset X and offset Y. During the zooming action, we will have both a scaling transformation and a translation action, whereas during the panning action, we will only have a translation action. The parameters offset X and Y can be defined by establishing a starting point with a mouse down action, which will then by adding to an incremental vector of delta X and Y during mouse movement actions. The parameters delta X and Y are obtained by subtracting the current mouse position from the initial mouse position, taking into account the current zooming scale. This is the subroutine to obtain mouse coordinates from word space coordinates, accounting for zooming and panning actions. This is the subroutine to obtain word space coordinates from mouse coordinates. A small subroutine to convert mouse coordinates into word coordinates based on the algorithm described above. To understand how it works, I will invoke it from the mouse down click event with the desired point coordinates. When I click the mouse button, this subroutine will be executed. Let me run the program and open a file. Now, as I click the mouse button, my subroutine will run and the coordinates of the point are 5.32, 0, and 1. In the following lines, I apply mouse zooming and panning actions. Since I didn't have any zoom or pan action, the offset is 0 and the scale is 1. These lines define the transformation matrix. Let's examine the transformation matrix members. As you can see, they match our hand calculations of the transformation matrix members. Let's continue running the program. In the next step, I multiply the transformation matrix by the word coordinates of the point to obtain the coordinates in the clip space. Now we have the Euclidean space coordinates of minus 0.435 and minus 0.089 and 1. Finally, in these two lines, I have converted the coordinates in Euclidean space into a coordinate of viewport space or MOS space, and we have viewport space coordinates of the MOS in pixels, which match the hand calculation of 214 and 425 pixels.